Today, I'll be talking about zero-instrumentation observability based on ebpf. Let's start from the very beginning. What is observability? Observability is being able to answer questions about the system. How is the system performing right now? How its current performance compares to the past period? Why are some requests failing? Or why are certain requests taking longer than expected? In other words, why system performs slower than before. A while ago, systems and web applications were much more simpler than today. Usually it was a dedicated node, means applications, maybe few replicas of applications, and a dedicated database. Pretty simple. If something goes wrong, you just will need to analyze logs of the application, maybe metrics of the application, or database metrics and logs. That's it. Pretty simple. Now, systems are getting more and more complex. Microservice architectures, a lot of databases. Usually, typical application this day can contain hundreds or even thousands of services, which are run on a Kubernetes cluster. Nodes are dynamic, which can appear and disappear, autoscaler, spot nodes, or something like that. While troubleshooting such a system, we need to follow the system topology from one service to another, to database, to infrastructure level, database level, network, a lot of stuff which should be analyzed to identify the root cause. Let's discuss the steps, how to integrate, make a system observable. What does it mean? The first step is collecting telemetry data, such as metrics, logs, traces, and force telemetry signal these days, continuous profiling data. If we do that manually, we should instrument every application with some observability framework, such as telemetry. This approach is good, but it requires time of your team. It can be time consuming because we have a lot of services. And the most, one of the additional disadvantages that you cannot achieve 100% coverage of such a system because of usually we have a lot of third-party services or legacy services. We cannot modify their code. That means we cannot integrate OpenTelemetry into such applications. Then we need to store somewhere this data. Usually it can be open source databases like ClickHouse or Grafana storages for telemetry data, or it can be some commercial services such as Datadog, New Relic, and so on, a lot of them. From my perspective, the most challenging part of this is learn how to extract insights from all this data, because we have 100 gigabytes or terabytes of logs. We have thousands or millions of metrics, and we have a lot of traces, how to analyze them and how to turn them into insights. What's happening with my systems right now, and how to understand the root cause of an issue using all this data. Our system is pretty complex, and we need to gather a lot of parameters or metrics or telemetry of each subsystem to be able to troubleshoot our application. And let's talk about what exactly we want to know about each application in our system. First of all, we need to understand how the particular application performs right now. It's called SLIs, service level indicators. Usually it means we want to know how many requests the system is processing right now, success rate or errors rate, and latency of each request, or it can be a histogram or something like that. any aggregation of latency will work. The second one, if we have a distributed system, we should understand how each component communicate with other services or databases. It means we need to know each outbound request to an external or internal service. We know how many requests is performing right now, success rate, and latency. We need to understand everything about resource consumption because any service can degrade or perform slower than usual if there will be a lack of CPU time, for example, or the application instance can be restarted because of out of memory, or if you run database, it's really sensitive to disk performance. Next, our components usually communicate using network. So we should understand how network is performing right now. So it can be some sort of network issues like connectivity loss between some nodes or availability zones or regions, if you're our system in many regions. There can be a packet loss or some network calls can proceed longer than usual because of delays at the network level. Then we should be able to explain why an application is limited CPU time. It can be, the reason behind this can be like the out of capacity of CPU on the node, or a node can fail or something like that. Then the next class of possible failure scenarios is something related to application runtime, such as JVM runtime, .NET runtime, or database internals. So we need to collect a lot of metrics related to the application runtime, such as garbage collector metrics, the state of thread pools or connection pools or logs, and so on. This telemetry will allow us to explain why, for example, a Java application stop handling requests for a while because of GC activity. Then, if we run our application in a Kubernetes cluster, we need to gather orchestrator-related metrics. Some of our application instances can be in unscheduled state. An orchestrator cannot place the application instance to the node because of out of capacity or something like that. Then to be able to investigate unknown issues like application-specific issues, we need to gather application logs. And the last one, I would say, is collecting profiling data to be able to explain why the particular application consume more, for example, CPU time than before. And knowing only CPU usage is not enough to understand the reason behind this. And as I see that there is two approaches to gather telemetry data. You can do it manually, or you can use some sort of automatic instrumentation using ebpf. The advantage of automatic instrumentation is that you don't need to change anything in your applications. You just need to initially install some agent, and that's it. You will have all telemetry data with some limitations, but we discussed it. And also, automatic instrumentations allows you to avoid blind spots. It means since you don't need to change code of your applications, you can instrument even legacy services or services that you don't have access to their code. It allows you to cover all your, but not only most critical services. But I've seen a lot of cases where companies started to add instrumentation into their applications, starting from the most critical services. And in fact, after a while, they have only a small part of their system instrumented telemetry data. And the last aspect is that manual instrumentation of your services, it's not a one-time project. It's a continuous process, because if you want to add a new service into your system, you will need to be sure that this service is also instrumented with OpenTelemetry SDK or something like that. Let's go deeper into what is ebpf and how it can be used to gather telemetry. ebpf is a feature of Linux kernel. Linux kernel allows you to run your own small programs in the kernel space. And such programs will be called some kernel function called or some userland function called. PF itself doesn't gather any data. It's just a way to instrument your system, but you have to write your own program and run it in the kernel space. It's pretty complicated task because kernel has a lot of limitations that apply to such programs. In simple terms, how we use ebpf? The first way is to attach our program to any kernel function call, such as, for example, open of a TCP connection. But this approach is not the best option because of possible compatibilities, because different kernel versions can have different function calls. The function can be renamed, deleted, and so on. So you need to support many variants of them. The second one, the kernel team tried to provide a pseudo-stable API to solve that problem. They inserted a set of trace points. Trace points is a statically defined places in the kernel code, and your ebpf program can attach to a trace point. And there are some guarantees that arguments of such trace points will not be changed over time. For example, at Caroot, we tried to use trace points and not use kpro. The third one option is upro, is a way to call your ebpf program when some userland function is called. For example, you have some binary file with Golang program, for example, and you want to attach to your program to calling crypto library, for example, and you can do with upros. And two things I want to mention here is the first one is maps. Your ebpf program can store some data in the kernel space using ebpf maps. You can keep some state between your program calls. Usually it's used to capture some data from one call and then use it from next program. For example, you open a TCP connection, and the first call you store a file descriptor in some map by process ID, for example. And then when connection goes to the established state, you can get the data from the map using process ID, for example, or other ID like socket. And the second one is turf maps. It's a way to share some data between the kernel space and the user space program. It's like a circle buffer, and it allows, for example, store some data in the kernel space and read this data from user space program. That's the main way to exchange data between the user land and kernel space. But it's a low level entities of ebpf. And I believe that you don't need to write ebpf program because there are a lot of ready-made, and Caroot is one of them. But I think it's good to know how it works, but you don't necessarily need to write your own ebpf programs. Now I'm going you about how caroot uses ebpf to gather telemetry data. We have our own node-agent. Node-agent is a Golang tool, open source, distributed under Apache 2.0 license. It's an open source agent that should be installed on every node in your cluster. It discovers processes, containers running on the node. It discovers their logs. We can analyze logs for repeated patterns. It tracks all TCP communications between processes, containers, and it also captures application level protocols data and can expose metrics and traces without any instrumentation. It supports the most popular protocols such as HTTP, Postgres, gRPC, Redis, Cassandra, and so on. And let's talk about how the agent uses ebpf. As I mentioned before, we try to use trace points. For example, to be able to discover new processes in the system, we call of trace point task new task. It allows us to know that in real time that a new process has been started, and we know its process ID, and then the user space part of the agent can resolve all metadata like cgroup of the process, understand the name of container, its labels, and so on. The second one is we capture events where some process is marked as a victim of their own killer. We need the data to understand the reasons why the particular process has been terminated. And on this call, on this event, we just put the flag into kernel space map that process with process ID 123 marked as a victim and will be terminated. And on the next call, when process is terminated, we can get this flag from the map and mark the event that goes to user land. That reason of the termination of this process is it has been terminated by the owner. And then we also track openings to be able to discover containers log, where container or process stores its log. And also we want to understand the actual storage partition a process communicates with. Then few trace points that we use to track TCP connections. The first one is syscall connect, where a process wants to open a new TCP connection. We call this system call, and we see that process ID 123 opens TCP connections to some destination, IP and port. Then, using socks set state at trace point, we can track the TCP handshake, and we can see if this TCP connection was successfully established or failed. We can track the errors of establishing TCP connections, and also we can track all successfully established TCP connections. And this last one is we track TCP retransmission associated with all connections in our system. It's really helpful to understand that service A communicates with service B slower than usual because of packet loss, for example. We need to retransmit our TCP segments, and it brings additional latency into communication process. And the last one is trace points that allows us to capture application level communications. The agent tracks that some process writes something to a file descriptor. Usually it's a socket, and we can capture a payload of such communications, and we can detect and parse application level protocols within such connections. We have two-phase application level protocol parsing. The first one is performed in the kernel space to like high performance protocol detection, but eBPF program is super limited in the ability to analyze something because it's like complexity. eBPF validator checks the complexity of each program, and for example, you cannot use loops in your eBPF programs. And if you want to parse protocol, like for example, to read payload or to extract URL of request or status of the response, we use user space protocol parsing, and we are not limited in our complexity of the program. So we can implement any logic. And the last one is about encryption, because these days, usually even communications inside your cluster should be encrypted by compliance requirement or something like that. And we need somehow to deal with that. There are two primary approaches to capture within encrypted TCP connections. The obvious way is to read the data before the encryption or after decryption, where you receive some response. In our agent, we support two ways to encryption, two types of program. The first one is programs that use OpenSSL library. It's, for example, or Python Pro applications or other interpreted languages. And the second one, we use a special uprob for capture Golang crypto library calls to capture data before the encryption. And it allows us to have pretty good coverage. So we can say that the agent 90% of data, even if it's encrypted. And few words about performance impact, because at first glance, it looks like a super crazy idea, allows users to run their programs in the kernel space, because kernel should perform like a low latency, and it's crazy idea if we have custom programs in the kernel space. But in fact, there are few guarantees from the kernel that allows us to run our programs without having significant performance impact. The first one is the validator in the kernel that validates every program before it runs, and it must have infinite complexity. You cannot use loops, and you cannot operate with huge amount of memory and so on. And it's super tricky to write your eBPF program that can be successfully validated by the validator. And the second thing that guarantees that performance of your eBPF program or your user space program will not affect the system is that communication between a kernel space and user space is occurred in using limited buffer. And if userland program will not receive some data because of a performance degradation or something like that, we just lose some data. And it will not bring some locking into kernel space. And from my perspective, it's pretty fair. And for observability purposes, it's enough, because I think it's more important to be sure that our system will not be impacted by our observability tool. But in worst case, we just lose some telemetry data. We will lose some traces or some metrics, but it's not a critical thing. As a result, we can instrument all our distributed system and understand how components of such a system communicate with each other, latency latency between any particular services, status of TCP connections between them, and so on. So we can have that, for example, front end communicate with services such as card, catalog, and so on. We can see latency, we can see number of requests. You will have all this service map just in few minutes after the installation. You don't need to change code of your application, integrate open telemetry SDK, and so on. And it's pretty useful for if you want to understand how the system performs right now. You cannot wait for a few weeks when your development team add some integration. And we have telemetry data, pretty granular telemetry data. It means we can track connections not between applications, but between any application instance with their peers. So we can see communications as with the utilization we need. For example, we can see how few Postgres instances communicate with each other. This is the primary instance, and the two replicas are connected to it for replication. And we know about each of that connections. We know the number of requests, the number of errors, latency of application level requests. We know how network performs between any instances. We know network round trip time. And we also know connection level metrics such as number of connections, number of failed connections, number of TCP retransmissions. It's pretty useful because in distributed systems, it's hard to understand what's happening right now, and it's hard to current topology of services. You should know the nodes where your application runs, and to check the connectivity between two services, you need to perform many applications to understand the topology, then goes to some pod to perform ping or something like that. And here we have telemetry data that already understands that an application can migrate between nodes and something like that. And it reflects the current picture of your system, current topology of your system. And also the agent provides not only metrics, it also provides ebpf-based traces. So we can see that we have, for example, application calls a database, and we can see that some of queries perform slower than others, and we can drill down and see particular requests and useful while troubleshooting. But ebpf tracing has some limitations. From my perspective, limitation is that ebpf traces are not actually traces. It's a individual spans, because when you instrument some application, open telemetry SDK, it can originate some tracing ID and propagate it to other services. As a result, you will have a single trace that contains all the requests from all services. In case of ebpf, we don't have a tracing ID, so we only can check the particular queries, and we cannot connect them to show you the whole trace. And yeah, there is some tool, open source tool that tried to solve that problem, and they use approach where they capture the request, then modify them, inserting, for example, trace ID header, and then send it. But from my perspective, it's not a good idea, because I believe that observability tools should observe. They shouldn't change your data. They shouldn't modify payload. And understanding this, we supported both methods of instrumentation in Caroot. We support open telemetry generated traces, and we also support ebpf-based traces for systems, for example, for legacy services and so on. After the installation, you will have ebpf-based tracing, but then you can enrich your telemetry data with open telemetry instrumentation. It's the best way to have all this data, and it allows you to extend your visibility of a system with ebpf-based data. And a few words about another way to gather telemetry data using ebpf. It's ebpf-based profiling. What is profiling? Profiling, it allows you to explain it allows you to answer the question what this particular application did at the time X, which code were executed and which code consumed more CPU, the most CPU consuming part of your application. ebpf-based approach doesn't require integrating some continuous profiling tools into your application. It doesn't require redeployment of your application. You just need to install the agent, and it will gather profiling data and storing it in some storage. In case of Caroot, we store all the telemetry data except metrics in ClickHouse. Here we have an example of how to use profiling data to explain CPU consumption. We can use CPU usage chart and select some area and see the flame graph, reflecting what part of your code consumed more CPU. In this case, it's example of coordinates component of Kubernetes, and we can see the particular function calls here. The wider frame on flame graph means corresponding code consumed more CPU than the smaller one. And also we can easily compare CPU usage within some CPU spike with previous period. And we can highlight, it's not a significant spike, but in this case, we can see the service having more DNS queries than before. And few notes on how Caroot works. You install the agent to your nodes. The agents gather telemetry data about all containers running on this particular node, their communication, they gather their logs and traces, profiles, and send them to Caroot, which stores metric, the parameters, and other telemetry signals in ClickHouse. Also, if you instrument your applications with OpenTelemetry, you use Caroot's endpoints that implements OTLP, OpenTelemetry protocol, and you can store telemetry data in the same storages. It's open source. Every component is open source, and you can use it. Or you can use Caroot Cloud to offload your storing telemetry data. And then let's just quick recap of the talk. ebpf is awesome, and it allows us to gather a lot of telemetry data without the need to instrument your code. And we can be sure that performance impact on your application is negligible. On our side, we have a page with benchmarks, so we understand the principles, but we decided to validate that using benchmark. If you want to gain visibility into your system, just in few minutes after the installation, just install Caroot. You can reach out to me on LinkedIn, Twitter. Thank you for your time.